All right, this is our last section of chapter 13, and this is actually going to be mostly a review of what we did in honors chemistry. You studied Le Chatelier's principle, and we're going to do that again. So first of all, let's just go over the principle. This states that when you have a system that is at equilibrium, you can put stress on it, and there are 3 different ways you can do that. And when you put the stress on it, it can force the reaction to shift, meaning that it'll go faster in one direction versus another. So once it's reached equilibrium, the rates are the same, but you can change that. You can force it to go out of equilibrium by putting stress on it. And then eventually it will reach equilibrium again. So the 3 ways that you can put stress on a system are to change the concentration, you can change the temperature, or if you have gases, you can change the pressure. And the stress doesn't always cause a shift, so we'll talk about for pressure in just a few minutes. If you have the same number of coefficients on both sides, then changing the pressure is not going to change a shift or cause a shift in equilibrium. But it could cause it to shift left or right to establish a new equilibrium. And so the first thing we're going to talk about is the concentration. First thing is to notice is what's highlighted in pink. Keep in mind that pure solids and liquids don't change the concentration. So if you add more solid, it's not going to affect equilibrium. It's not going to shift the reaction. But if you increase or decrease them, it can cause a shift. And if you increase something, it's going to shift away from that thing. And if you decrease something, it's going to shift towards that thing. So for example, if you increase the reactants, it's going to shift towards the products. If you decrease the reactants, it will shift back towards the reactants. For changes in temperature, the first thing you want to do is to put heat into the reaction. So sometimes it'll be in the reaction for you. So if you had something like you have this reaction, sometimes it'll just say heat in the reaction. Or sometimes it'll say, this is going to be 3 different ways that you can say the same things. It could put the actual amount of heat in there, so 65 kilojoules. It also could put it off to the side with a delta H. And if it's off to the side, you need to put it in the reaction itself, and you're going to use the sign to figure out which side. So if a negative means you're going to put it on the product side, and if it's a positive delta H, then you're going to put it on the reactant side. Because remember, negative delta H means it's exothermic, so heat is coming out of it, so you're going to put that on the product side. Positive delta H means it's a reactant, means it's going into the reaction. And then once heat is in the reaction, once you have it on the reactant or product side, you can figure out which way the reaction shifts the same way you did as change in concentration. So if you add heat, it's going to shift it away from the heat. If you take away heat, it will shift towards the heat. And sometimes they'll just tell you that it's exo or endothermic. So you need to know that if it's exo, then heat is on the product side, and endo means it's on the reactant side. Keep in mind, this is important, notice what's highlighted in pink, that changes in temperature will also change K. And actually temperature is the only thing that will affect K. You need to write that down somewhere in your notes, make sure you highlight that. It's really important. It's a common AP multiple choice question, and it's a common question in essays as well. So the only thing that will affect K is temperature. And you can figure out what happens to K based on what's going on with temperature. So if you remember that K is equal to products over reactants, so if you decide, based on Le Chatelier's principle, that because of a temperature change, the reaction is shifting towards the products, well, products are on the top of the fraction, so that means K is getting bigger, because as the top of the fraction gets bigger, so does K. If you decide that because of a temperature change, the reaction is shifting to the left, so let's say that it's, if we go back to these reactions over here, and we say that we're increasing the heat is going to shift the reaction back to the left. And in that case, we're going to increase the amount of reactants, which are on the bottom of the fraction. And if the number on the bottom of the fraction gets bigger, then the value of K is actually going to get smaller. They're inversely related. So you can figure out what happens to K based on which direction it's shifting. And then the last one is pressure. And again, this will only affect gases. So you have to have gases in the reaction. And as you increase the pressure on something, it's going to shift to relieve the pressure. So if you increase the pressure, it's going to shift towards the side with fewer moles so that it's not as crowded. So you can think of it as being crowded or lonely is the way we teach it in honors chemistry, even though you have to understand that particles do not have feelings. They don't really feel crowded or lonely. That's just how we kind of think of it. So the reaction is, if you increase the pressure, it's going to shift towards the side with fewer moles. And if you decrease the pressure, it's going to shift towards the side with more moles. And when I say moles, I'm talking about the coefficients. So if you had like 2A plus 3B yields 3AB, if you had something like this. I mean, I know it's not balanced, but just say you had these coefficients. So notice that we have a total of 5 on the left and we have 3 on the right. So if you increase the pressure of this system, it would shift to the right. Should be an arrow, not an equal sign. It would shift to the right to relieve that pressure. And if you decrease the pressure, you're going to have more space, so it's going to shift towards the side with more particles. So you can't memorize which direction it is going to be because it's going to depend on the reaction itself and the coefficients. And volume is related to pressure. So you could talk about volume as well. So increasing the volume of the container is going to decrease the total pressure. And so the reaction will shift towards the more moles. Decreasing the volume is going to increase the pressure, so it's going to shift towards fewer moles. And then you do want to make a note of these highlighted things here. So inert means not involved in the reaction. So sometimes you'll hear noble gases called inert gases because they don't react with things. So if an inert gas is added at constant pressure, then the volume will increase to accommodate the added gas, and therefore will decrease the overall pressure, so equilibrium will shift towards the side with more moles. If the inert gas is added at constant volume, so if the container can't change size, the concentrations and partial pressures of the reactants and products are not going to change because they're still hitting the walls of the container the same amount, and so therefore there's no change in equilibrium. So the time that an inert gas can affect it is if the volume can change. So if you had something like a balloon that can change its volume, that can change the volume of everything, the reactants and the products. But if the volume doesn't change, if it's a rigid container, then there's going to be no change in equilibrium. And then the last thing is to just mention catalysts again. So keep in mind that catalysts will speed up how fast something can reach equilibrium, but they don't actually change equilibrium, the point itself. They don't change the different concentrations that would have to be achieved in order to reach equilibrium. So they don't affect equilibrium except that they speed up the process of reaching equilibrium if you have something that's not at equilibrium. And that is it for chapter 13.